So first let's discuss what is leaderless replication and how it works. So if you recall the multi-leader replication system, the writes were going to either one of the leaders, and the leader who is receiving the write is responsible for propagating the changes to other leaders, right? So the leader had additional responsibilities of not just taking writes but also to propagate. But in leaderless system, every node is independent and there is no concept of leader, right? So these nodes are not responsible for propagating the changes or keeping them in sync or anything like that, right? So how does this work? So the web servers or the clients, whoever it may be, are sending the updates or writes to all the nodes that are available in the system, right? Not just one node, like in the case of multi-leader or single leader. They will send the updates to all the nodes. And while reading as well, they're going to read from all the nodes. They're going to make the same query for all the nodes and get the responses and see whichever node is giving the latest response, they're going to use that, right? So that is how the leaderless replication system works. So among these nodes, there is no communication with respect to propagation. There are no logs being sent for every write or update, but they are communicating with each other using gossip protocol to just do a health check if the other nodes are alive, and also to check if there is any staleness in data, right? So if there is some staleness, there are ways to handle it, which we will discuss in some time. But the whole idea is to keep them independent from each other as much as possible, and they can independently work on reading the writes and saving them in their own local database, right? So that is how leaderless replication works. Now let's discuss some more points on this. So we have seen what is leaderless replication. Let's see where we might use such a leaderless system. So here are some examples. So in a caching system or IoT or messaging pub/sub event system or in analytics, we can use this leaderless replication. These are systems where the write order does not matter as much, right? And even if there is some delay in the writes, it is still okay. So we are okay with eventual consistency here, but also with some staleness of data. So if you think about analytic streams, the event streams can come in any order, and analytics can use internal mechanisms to run some number crunching and stuff like that. But the incoming streams themselves need not be in the correct order, right? So there is no write order guarantee that is required here. Similarly, for publisher-subscriber systems, publishers can be sending events in any random order and subscribers will consume them in a different order, right? So in these kind of situations as well, we can think of suggesting leaderless replication, right? So the leaderless replication concept is built on some Dynamo principles. So this was a paper given by Amazon way back in 2007, I think. And there are some principles which are prominent in using leaderless replication. So let's have a look at them. So there's a nice Wikipedia article that I'll leave the link in the description below for you to check out if you're interested. But here are the principles with respect to Dynamo storage system, right? So the first principle is incremental scalability. Dynamo should be able to scale out one storage host at a time with minimal impact on both operators and the system itself. So here it is saying that we should be able to add one node at a time without having a major impact on the entire system, right? And symmetry. Every node in Dynamo should have the same set of responsibilities as its peers. There should be no distinguished node or nodes that take special roles or extra set of responsibilities, right? Like we discussed in the diagram, every node is treated independently and they all have the same set of responsibilities and they act independent of each other. The third one is decentralization. An extension of symmetry, the design should favor decentralized peer-to-peer techniques over centralized control, right? So in this leaderless replication system, there is no coordinator or any centralized control over all the nodes. The nodes are independent of each other, and this is a very good example of decentralization. And heterogeneity. The system should be able to exploit heterogeneity in the infrastructure it runs on. For example, the work distribution must be proportional to the capabilities of the individual servers. This is essential in adding new nodes with higher capacity without having to upgrade all hosts at once, right? So here it is saying that we should be able to leverage the multiple nodes that we have and not just keep them for the sake of it. And if we are adding a new node, we should be able to exploit that as well, right? So these are some fundamental principles behind the Dynamo storage system, right? So the main paper that describes all this is, I think, available here. If you're interested, definitely check out this link. We'll go back to our whiteboard now. So we discussed the Dynamo principles, which are the foundation for leaderless replication. Now let's see what happens during a failover. So for this, let's take the help of this diagram. So the timeline goes from left to right, and user 1234 is trying to set a new profile picture for himself. And like we discussed in leaderless replication, the update should go to all the replicas. And here we have 3 replicas, and the user is sending the request to all 3 replicas. And here we can see replica 1 has responded okay, replica 2 has responded okay, but replica 3 is offline. It is not available. So what happens when another user reads it? The user is also reading from all the 3 replicas, and from replica 3 we get version 6, which is the old image, and from replica 2 and replica 1 we get version 7, which is the new image. So because there is a mismatch in the versions, the user 2345 can pick the latest version, which is version 7, and use it. And because this user has seen that replica 3 is little outdated, this user will send a new update request to replica 3 to make itself up to date with the latest version, right? So this is one way of handling a failover. So this process of handling a failover during a read is called read repair. So the system that we just saw is called read repair. But if you think about it, this is very client dependent. So if there is an update that is not updated in one of the replicas and nobody ever reads it, then that replica is always in that stale state, right? Outdated state, and there is no coming back from that. Right? So that is the downside of read repair system. There is another system called anti-entropy. This is simply a background system. This runs in the background, and this is done internally between the nodes to check if there is any difference or staleness in data, and if there is any, the updates are sent. Only those updates are sent to the other node so that everybody is in sync, right? So this is different from the catch-up mechanism that we saw during single leader or multi-leader, where the leader is sending the entire log with timestamps to the other one, and the follower is actually executing one query at a time to update itself. So there is no log sending mechanism in this leaderless system, but it uses a concept called Merkle tree to find the difference between the current state and the other node, and only those differences will be updated, right? So we will discuss Merkle tree and how this data structure works and why it's so efficient in terms of time complexity in a future video. But for now, just understand that the anti-entropy system is some background process that is running in the nodes, and they are checking with each other and keeping themselves up to date, right? Another subtle difference to understand is that in leaderless replication, there is no rollback. For example, we have replica 1 committed that the write is okay, replica 2 has committed that the write is okay, but replica 3 is offline. This does not mean that replica 1 and 2 are going to roll back themselves. So they're going to keep their state, and it is only after maybe read repair or anti-entropy that the other node will be updated, right? So the previous nodes will not be rolled back. So again, in these type of systems where we are using event-driven publisher, subscriber, or analytics, it is not so critical that the write order matters. So that is how failover handling works in leaderless replication. Now let's see quorums for read and write. What happens with these multiple nodes? So let's say we have 5 replicas, replica 1, 2, 3, 4, 5. So for a write to be considered a successful write, there needs to be at least 3 replicas which are successful, which have committed that they have received the write. And for a read to be successful, we need at least 3 replicas to say that they have successfully having the latest version of the data. So in other words, if you look at it, there should be at least 1 replica which is an overlap between the reads and writes, so whoever is reading the data can be assured that they are reading the latest state of the data, because one of the replicas has the latest version, and even if other replicas don't have the latest version, we can see which version is latest while reading from all replicas and keep that and update the remaining replicas, right? So in this way, the quorum works in leaderless replication system. Now let's see some examples. So like I said, there are databases which follow the Dynamo principles and Dynamo style. So a couple of examples are Riak and Cassandra. And you might be thinking Amazon DynamoDB should be one of the examples, but in reality, DynamoDB uses single leader or multi-leader, but definitely not leaderless replication, right? So the paper was introduced by Amazon long time ago, but DynamoDB in itself is not a leaderless replication database. Okay, so finally, when to use this? Like we discussed, this is very good when write order isn't critical and you need high availability and low latency, and we are okay with eventual consistency, right? So even if there is some staleness in data or delay in data updation, we are okay with using leaderless replication. Okay, so we've covered all the replication system, guys. If you have any questions, definitely let me know in the comment below. And if you need any further info about anything that we've discussed so far, definitely let me know in the comment below. I can share some resources or cover them in a future video, right? Thank you so much for watching. I will see you in the next video. Do subscribe if you haven't done already. Do leave a like if you found this helpful. Thank you so much for watching. Cheers.